Hello everybody. In this video, I want to talk a little bit about the difference between intra and intermolecular forces. So intramolecular forces, intra means inside. So these are forces that are occurring within a single molecule. And inter means between. These are the type of forces that are happening between different molecules. So say two different molecules interacting with one another will have intermolecular forces. So intramolecular forces again are forces that are present within the same molecule. And as a little example here, I have drawn out sulfamic acid, which is what they call a Zwitter ion. And Zwitter ions are pretty important in biochemistry. Amino acids that make up proteins can be a Zwitter ion under certain conditions. And what that means is that it has both a negative charge on it, on one part of it, and a positive charge on the other. So let's talk about all of our intramolecular forces here. All of these covalent bonds are intramolecular forces. They're holding this molecule together. But in addition to that, we have the attraction of this positive species here and this negative species here. They're going to attract one another across distance, but this distance is going to be pretty short because we're talking about a single molecule, and therefore it's going to be a pretty strong interaction as opposed to the type of interaction we're going to see later with ions, where we have two different species that can be quite a bit of distance away from one another. So just to review here real quick, intramolecular forces typically involve interactions over short distances. Short distance interactions can be very strong. So next we have intermolecular forces. And we have different types of intermolecular forces. Our first one being ion-ion. This is the intermolecular force that's leading to ionic bonding that we've seen before. And we know this to be a very strong interaction that can actually be considered a true chemical bond. Next, we're going to have ion-dipole. And if you think back to when we talked about dissociation of ionic compounds in water, that's what's happening here. The dipoles of the water molecules are arranging themselves towards the positive cations and away from the negative anions. And this actually is what has allowed them to stabilize and separate from one another and gain some distance between each other. Is a stabilizing effect from these partial negative charges and partial positive charges on the water molecules. Next, we have dipole-dipole interactions. So when our molecule has a dipole, we know that there's going to be a partial negative charge on one of them and a partial positive charge on the other one. In this case, we've seen that chlorine is going to have a partial negative charge and hydrogen is going to have a partial positive charge. And these two are going to arrange themselves such that the dipole from this guy is going to point towards the beginning of the dipole of the next guy, and they're going to have an interaction over distance. Next, and probably the weakest of any interaction that pretty much we don't really take into account unless we don't have any of these other interactions, is something called the London dispersion forces or the van der Waals forces. And basically what happens here, for instance here I've drawn out propane. When we don't have any of those other interactions, but the molecules are still getting close enough to one another, they start to shift electron density away from one another. So what's going to happen ultimately is the electrons in this guy, if it gets close enough here, are going to repel them to the other side of the propane molecule, leading to a very slight partial positive charge on this end. And then the electrons here are going to be attracted to that, and they're going to create their own partial negative charge closer to this one, and we start to see interactions between the molecules. Next, we have hydrogen bonding. And what this is a special case of dipole-dipole interactions that include hydrogen. And these hydrogen bonds are stronger than your typical dipole-dipole interactions. And that's because hydrogen only has one electron. So if we start to shift that electron away from it, it'll take on more of a positive charge than one might expect. And this is what is holding together water molecules. So if we consider other molecules that are roughly the same size as water, they're all gases. Oxygen is actually heavier than water, so is nitrogen. Most of the other ones, I can list tons and tons of gases that are all going to be heavier than a water molecule, yet water is a liquid. And that is due to these interactions where the dipole from one water molecule is attracted to the hydrogen on another one. And because this is a special case of hydrogen bonding, these interactions are going to be pretty strong. It's going to pull them all together, and it starts to form water into a liquid as it builds out this whole lattice of hydrogen interactions. Most typically, you're going to see hydrogen bonding between oxygen and hydrogen. So anytime you see an oxygen and a hydrogen, you'll suspect that there may be some hydrogen bonding going on. Water is your classic example, but also pretty much all of the alcohols, methanol, ethanol, isopropanol, like rubbing alcohol and stuff, they're also going to have hydrogen bonding happening. So with what we now know about intermolecular forces, I want to re-examine what we were talking about before with the phases. So in a solid, the intermolecular forces are so strong that it locks the atoms in a crystalline lattice. This means that there's going to be a regular repeating pattern to the atoms that exist in there. And the only movement that's going to be allowed is just vibration. They can't break out of their spot. They're just kind of vibrating in place there. In a liquid, the atoms have enough energy now that they are able to move far enough apart from one another to rearrange freely, but they are not so far away from each other as to negate the intermolecular interactions. And so our image of this is the atoms are still interacting with one another, but they are able to move in between one another and rearrange in this fashion. That's why liquids can change their shape, but they're not going to change their volume. In average, these atoms are going to remain roughly the same distance from one another. And I think it's important to note that being a liquid is really a balance between solid and gas. And if you think about it, you can get very, very cold. There's a very wide range of cold that can happen where everything is still a solid. And once you become a gas, you can continue to heat that gas till it's very, very hot. And it'll remain a gas. But there's only a narrow temperature range where we see stable liquids. Even though they're very ubiquitous around us, it's more a consequence of the fact that if we weren't near those types of temperatures, then we wouldn't have liquids and we wouldn't have life. Then it is true that across the universe, liquids are very prevalent. Once we have gases, gases are moving rapidly in free-moving trajectories. They are far enough away. Look, I can't even spell moving. Oop. There we go. They are far enough away from one another to have only negligible intermolecular forces. So they're not really interacting with one another. And we're going to see later that we actually make some approximations that for gases that hold pretty well, that say that they don't interact with one another at all. So there's not really like this guy's feeling the intermolecular forces of this guy. They're all just moving independently, banging around and stuff. And that's why the gases are able to change their volume. They just go ahead and continue to move in straight lines as far as they can, wherever they can. Not really being deflected in any way by one another. So let's think about the change of phase with temperature from an intermolecular forces situation. So increasing the temperature increases the average kinetic energy or velocity of each of these guys. So they're going to start moving faster of the atoms. When the kinetic energy is high enough, the atoms gain enough energy to overcome the forces holding them together, and they start to move from a solid to a liquid to a gas.